All right, welcome back. This is our 6th lesson on radical expressions, and today we're going to be investigating the difference between radical form and exponential form. Now, if I write on the board the square root of x, we read this is called radical form. We read this as x to the first power, and our index is 2. So remember that we are dividing exponents. This is x to the 1 divided by 2 power. If I write the cubed root of x, this is x to the 1 divided by 3 power. Notice exponent of 1 underneath. We're taking the exponent underneath and dividing by the index. Now I want you to recognize, what is our index? Index lies on the bottom in exponential form, or it lies in the denominator. Notice, what is our index? Index is 3. It lies on the bottom. Now if I write the fourth root of x to the third, we read this in this is radical form. We read this in exponential form as x to the 3 divided by 4 power. Now going backwards. Well, I guess we'll investigate going backwards in a moment. But before we get started, I guess, with the lesson, let's go ahead and remind ourselves that radical expressions refer to laws of exponents. Laws of exponents. And we're going to actually add more rules to this list, some sub-rules to the laws of exponents as we go through the exponential form of radicals. Laws of exponents refer to the operation of multiplication. And we are first looking at if the bases match and we are multiplying x to the second power multiplied by x to the third power. If the bases match and we are multiplying, we add the exponents. This is x to the fifth power divided by x squared. So if the bases match, x matches x, and we are dividing, we subtract the exponents. This is x to the third power. And we also have x squared to the third power. If we have power of power, we will multiply the exponents, giving x to the sixth. And lastly, we have addition, subtraction, multiplication. Remember that radical expressions refer to the branch of division of exponents. And so if we're looking at the sixth root of x to the 18th, remember that this is 18, x to the 18 divided by 6. Or in this case, we look at even divided by even. Even divided by even results in odd. This is absolute value of x cubed. So these are our 4 main properties of the laws of exponents. Remember, we are counting the number of times in which we multiplied, but I'm actually going to add more to this list, more sub-properties of the laws of exponents as we go through radical exponential form of the radical expressions. Now, so let's go ahead and dive right into the problems. The first set of exercises is practice going back and forth between forms. So problem number 1, and I'm just going to leave this up here. Problem number 1, we're converting back and forth from radical to exponential form. So problem number 1 says 5 to the 1/3 power. Okay, so we're looking here at exponential form. And remember that our index lies on the bottom. So we're going to circle the 3. Let me write that a little more clearly. 5 to the 1/3 power. Okay, remember our index lies on the bottom, so we circle the 3. This means the cubed root of 5 to the first power, and we don't have to write the 1, so we just read this as the cubed root of 5. Now, number 2 is 6 to the 2/5 power. We read this as an index of 5. So circle the 5. This is your index. We read this as the 5th root of 6 squared. Now, this is not the final answer. Remember, we are simplifying radical expressions. And simplify, if I can spell. Simplify means to add, subtract, multiply, and divide. So we add, subtract, multiply, and divide until we cannot do this anymore. So we're looking at the 5th root of 6 squared. We can now square the 6. We can multiply 6 by itself and get the 5th root of 36. Now, number 3 says m to the 4/7 power. Okay, so our index lies where? On the bottom. This is our exponential form. We're going to convert back to radical form. So this is the 7th root of m to the 4th. Now, lastly, we have number 4, n cubed to the 2/5 power. Notice in this case, we're going to have to use a law of exponents here. So we look at, what do we do with our exponents when we have power of power? So notice we have power of power here. We multiply our exponents. So we're actually going to multiply 3 times 2/5. One more time, 3 times 2/5. Reminder, this is 3 over 1 times 2 over 5. So the 3 multiplies by which number? The 3 multiplies by the top. 3 times 2 gives 6, and 1 times 5 gives 5. Notice that the denominator did not change. So I want you guys to just practice. 3 times 2/5 is just simply to say we can multiply the 3 by the 2, and get n to the 6 over 5. Notice the index does not change. So we end up with 3 over 1 times 2 over 5, 3 times the 2, 1 times the 5 gives 6 over 5. Now, n to the 6/5. I want you to notice something about the problems up here. Notice, our numerator was smaller than our denominator, so we ended up with 1 5. Numerator was smaller than the denominator, so we ended up with 2 6s. Notice, if we were looking at cubed root, we would want to take out a group of 3. So we're still simplifying by taking out groups. Can we take out a group of 3 5s? No. Why? Because the numerator was smaller than the denominator. Notice here, can we take out a group of 5 6s? No. Why not? Because the numerator is smaller than the denominator. And notice, can we take out a group of 7 m's? No, because 4 is smaller than 7, which means our numerator is smaller than our denominator. Down here, though, we have n to the 6/5. I want you to notice our index is 5. We end up with the 5th root of n to the 6th. But since our numerator is larger than our denominator, we can then take out a group. So since we have 6 n's, we can take out one group of 5 n's, leaving one group becomes 1 n on the outside, and underneath the 5th root, we have just an extra n left. So we took out 5. There's just 1 n left. Now, all right, number 5, we're going backwards. So we're going to give the radical form, go back to exponential form. So 5 through 8 on this practice sheet. Well, I guess 5 through 7 is probably all we'll look at, because I think you're getting comfortable with this. This was actually covered in the snow day videos. But I'm just being a little more specific about the numerator being larger or smaller than the denominator. Here we have the square root of 79. Now, we're going to convert from radical form back to exponential form. We notice that our exponent here is a 1 and our index is a 2, so we're going to write this as 79. Remember that the index goes on the bottom, so this is 1 divided by 2, 79 to the 1/2 power. The 4th root of 153 is read as 153 to the, well, exponent is 1, index is 4. Remember, index goes on the bottom. This is 1 divided by 4. We're looking at cubed root of 27, m to the 6th, n to the 4th. And in this case, notice, we could not break down the 79 because 79 is prime. If we try to break down 79, 79 is just 1 times 79. 153 is also a prime number. Well, actually, it's not prime. I'm sorry. It's 3 times 51, 3 times 17. It's not prime. I'm sorry. But there are 2 3's and 117 that multiply to give 153. Now, we're trying to take out groups of 4. The reason I didn't ask you guys to factor this, and I should have said something about this, is that there is not a group of 4 factors in 153. So we cannot take out, if I write 3 times 3 times 17, we cannot take out a group of 4. So we're stuck. So we just simply write 153 to the 1/4. However, 27 can be broken down into a group of 3. Notice we're taking out groups of 3. So take 27, break it down. This is 3 times 9, which is what? 3 times 3. So we're going to write this as the cubed root of 27 is 3 3's. So 3 to the 3rd power, n to the 6th power, n to the 4th power. Now, 3 to the 3rd. We're going to write this in exponential form as 3 to the 3 divided by 3, n to the 6 divided by 3, and n to the 4 divided by 3. Now, notice we can reduce two of the exponents here and get 3 to the 1st power. Notice 3 divided by 3 is a 1. We don't write the 1. n to the 2nd power, and here 4 divided by 3 stays 4 divided by 3. Did I write m? This is an m. Okay, so m, I'm sorry. M, 6 divided by 3 is m squared, and n to the 4 divided by 3. So we're done here. Now, all right, number 18. Okay, so we're going to move away from going back and forth from radical to exponential for a moment, and we're going to establish a rule for this lesson. The rule for this lesson is that final answers. We're working in exponential form, but final answers must be written in radical form. Now, if you remember on the snow day video, I talked about 3 forms, the difference between exponential form, radical form, and simplified radical form. So we're going to be identifying these different forms as we go through this lesson. So number 18 says g to the 4/7 multiplied by g to the 3/7. And since we're in exponential form, we're going to be using our laws of exponents. Now, reminder, when the bases match and we are multiplying, what do we do with the exponents? We add. So here we have 4/7 plus 3/7 gives g to the 7/7. And now final answers go in radical form, but in this case you notice that 7 divided by 7 is 1. So we end up with g to the first power. We don't have to write the 1, and this is our final answer. Now, we will have to watch out for absolute value, although in this case we have odd divided by odd, so there is no need for absolute value in this case. Number 19 is s to the 3/4 power multiplied by s to the 13/4 power. And notice when the bases match, we are adding our exponents. So in this case, 2 plus 3 gives 5. Okay, so here we're going to do 3/4 plus 13/4. Reminder, when we're adding fractions, I should have said this in the last one, we have to have a common denominator. So 4/7 plus 3/7. Notice, when we add, something must match, and what matches doesn't change. Since the denominators match, the denominator will not change. The denominator is a 7. And we add what's on top. 4 plus 3 gives 7. Notice that the denominator did not change, and 7/7 is 1. So we look here, and question is, do we have a common denominator? Yes, we are multiplying, the bases match, we're adding the exponents. Since the denominators match, the denominator will not change. Or I should say this, we know that the denominator represents index. So we're going to look at this in radical form in a moment. So another way of saying this is that the index must match. Now we're going to add the numerator. 3 plus 13 gives 16/4. And now we can divide. 16 divided by 4 gives 4. So we have s to the 4th. And there is no absolute value in this case. If you're struggling with the concept of when absolute value occurs, when absolute value does not occur, you can go back and watch the radical absolute value video posted, I think, 2 videos before this. But here, even divided by even gives even is definitely not absolute value. Now, another way of looking at this is the 4th root of s to the 3rd power multiplied by the 4th root of s to the 13th. Now notice that we're looking at 3/4 power. Can you see 3/4 here? So you should be able to see a fraction 3/4, and you should be able to see a fraction 13/4. Notice, when we add fractions, 3/4 and 13/4, remember that the denominator must match. So another way of saying this is that in order to multiply radicals, what has to match? The index has to match. And this is the 4th root of s to the 16th, which is, now take out 4 groups, we end up with s to the 4th. Now, all right, but we're primarily working in exponential form. Now you're going to start seeing answers have to be converted back to radical form. Number 20, I'm using a practice sheet here that you should have received in class. Now, u to the 1/3, all this to the 4/5 power. Notice, in this case, we have power of power. Reminder, when we have power of power, we multiply our exponents. So 2 times 3 gives 6. In this case over here, notice we have 1/3 and 4/5. We are going to multiply our exponents. When we multiply fractions, we multiply top times top, bottom times bottom. So this is u to the, if we're looking at 1/3 times 4/5, remember 1 times 4 is 4, 3 times 5 is 15, so we get 4/15. So multiplying is definitely easy because nothing has to match and everything changes. 1 times 4 is 4, 3 times 5 is 15. Now notice, we end up with an answer in exponential form that cannot be, the fraction cannot be reduced. So we have to convert final answers to radical form. So we're going to convert this. Remember that 15 is our index. So we're going to write this as the 15th root of u to the 4th. Now question, can we take out a group? Remember, we're taking out, in this case, groups of 15. Well, we only have 4 u's. You cannot take out a group. Why? Because in order to take out a group, the numerator must be larger than the denominator. Since our numerator is smaller, we cannot take out a group of 15 u's. So we are finished. This is the final answer. Now, number 21. Okay, so now we're going to start looking back in the previous lessons at concepts of rationalizing denominators. So let's look at this as y to the negative 1/2 power. Remember that the rules of simplification, there are some additional rules added. First, we cannot have negative exponents in the final answer. So no negative exponents in the final answer. So the first thing we have to do, and these rules are not written in the book, but you just have to understand that these rules are part of the rules of simplification. So no negative exponents in the final answer means if you see a negative exponent, you have to get rid of it immediately. Reminder, 3 to the negative 2 power means move it where? Move it to the denominator. This is 1 over 3 squared. Or another way of thinking of negative exponents is change multiplication to division. But right now we're just going to think of shifting from numerator to denominator. So question, does 3 to the negative 2 power represent a negative number? No. It represents 1 over 9, which is a positive number. Remember that negative exponents mean shift position with respect to numerator or denominator, but they do not refer to negative values. If I say 3 to the negative 1 power, this means move 3 to the negative 1 to the denominator. This is 1 over 3 to the first power, and the exponent changes sign. Similarly, if I say 1 over x to the negative 2 power, you can move x to the negative 2 power back to the top and get that this is x to the positive 2 power over 1, and we don't write the denominator of 1, so we just say that 1 over x to the negative 2 is x squared. Now, looking at y to the negative 1/2 power, we can move this to the denominator and say that this is 1 over y to the 1/2 power. Now, remember that final answers have to be in radical form, so we're going to convert this as 1 over, notice our index is 2, the square root of y. We cannot take out a group because our numerator is smaller than our denominator. However, are we done at this point? Hopefully you recognize this and say no. There is another hidden rule with the word simplify, and the other hidden rule is that we must rationalize all denominators. What does this mean? Rationalize all denominators means, again, this was covered in the previous lesson, to get rid of any radicals, or I should say maybe this. Rationalize denominators means, we'll say that. Get rid of the radicals in the denominator. AKA, no roots, or no exponents, no fractional exponents in the denominator. Okay, so we're looking at 1 over the square root of y. Notice we have a radical in the denominator. We have to get this out. Reminding you, we have an index of 2, and we would like to take out a group. So what we're going to do to get this radical out is we're going to create a group that can come out. Since the index is 2, how many y's do we need total? We need 2. So we need a total of 2 y's, but how many y's do we only have? We only have 1. So how many more y's do we need to create a group of 2? We only need 1 more. So we're going to multiply by square root. Square root, remember that in order to multiply radicals, the index must match, or the denominator of the fractions must match. So we have to multiply. If this is square root, we have to multiply by square root. We have 1 y, we need 1 more y. So we're going to multiply by square root y, on top and bottom. Whatever you do to the bottom, you must do to the top. We end up with the square root of y squared, and on top, 1 times the square root of y is the square root of y. Now, on the bottom, notice we have a group of 2 y's that can now come out. We end up with the square root of y over, take a group of 2 y's out, we are left with a y on the outside, and no y's left under the radical, so we do not write the radical. Question, have we successfully gotten the root out of the denominator? Yes. Notice that the final answer has no root in the denominator, and this is considered fully simplified. Now, next question. Next question is b to the 3/5, 22. b to the 3/5 power. We look at this and say, well, the rules are to simplify. That means take out groups, add, subtract, multiply, and divide, no negative exponents in final answer, and rationalize all denominators. You look at this and you say, well, there's no groups to take out because the numerator is smaller than the denominator. There are no negative exponents. This is not in the denominator. This is where? This is in the numerator. So there's really nothing to do here. There's nothing to simplify. So what are you supposed to do with this? Really nothing. This is already simplified. However, I said in this class I want all answers or final answers in radical form. So we're going to convert this to the fifth root of b to the third power. Now, okay, so we're looking now at number 23. Q to the 3/5 power divided by q to the 2/5 power. Okay, so now we're looking at division. Okay, so reminding you, when we have division and the bases match, what do we do with the exponents? We subtract them. So 5 minus 2 gives 3 in this case. Over here, we're going to take the exponent 3/5 and subtract the exponent 2/5. Since q matches q, or our bases match, we end up with q to the 3/5 subtract 2/5. And this results in q. Notice that in order to subtract fractions, the denominator must match. Notice that our denominator matches our denominator. So this is q to the, notice, 3/5 minus 2/5. The denominator will not change when we add or subtract. So this is the denominator 5. 3 minus 2 is 1. So we end up with q to the 1/5. Now, question, are there going to be groups that come out? No. Why? Because the numerator is smaller than the denominator. However, we need to write our final answer in radical form, so this is the fifth root of q to the first power. Now, let's look at another example, a sub-example that I've created, q to the 2/5 divided by q to the 3/5, and this is not on your sheet. I want you to notice something different about this problem. Now, before we do this problem, you have to understand that when we subtract exponents, look over here for a minute. When I say x to the 5th divided by x to the 3rd, when we subtract exponents, we end up with x to the 5 minus 3. Where does our result lie after subtraction? Well, after subtraction, our result lies in the numerator. This results in x to the second power over 1. So after subtracting exponents, your result lies in the numerator, not the denominator. So regardless of whether we subtract and get a positive exponent or whether we subtract and get a negative exponent, the result will always lie in the numerator. Let me show it like this. Let's go ahead and do x to the third power divided by x to the 5th. Okay, before we subtract, maybe do this first, because you guys are familiar with canceling. So x to the 5th divided by x to the 3rd, we think of this as 3x's canceled with 5x's, leaving how many x's? Well, hopefully you say 2x's where? In the numerator. So we end up with x squared. However, if I write x to the 3rd divided by x to the 5th, notice if we cancel 3x's with 5x's, we have 2x's left over. But where are these 2x's left over? They're left over in the denominator. So we have nothing left on top. We write a 1. So we end up with 1 over x squared. Now let's look at this in terms of subtracting. So 5 minus 3 gives x squared. Where does our result lie? Our result lies in the numerator. So let me write this as 5 minus 3. And we're going to write this over 1. So this is x to the second power over 1. Now, if we do 3 minus 5, okay, so this is a little tricky. If we subtract exponents, 3 minus 5, we get x to the 3 minus 5. And where does the result lie? Whenever we subtract, the result lies in the numerator. So we end up with x to the negative 2 power lying in the numerator. Now, we have to then convert the negative exponent to a positive exponent and move this back to the denominator. So this is 1 over x squared. So we take the x to negative 2, move it to the bottom. This is 1 over x squared. So looking here, if we're going to subtract the exponents, where will the result lie after we subtract? The result will lie in the numerator, in the top. So this is q to the 2/5 minus 3/5. Notice that 2/5 minus 3/5, the denominator matches. The denominator will not change. So we have a denominator of 5. 2 minus 3 gives negative 1. Now, we get a negative exponent, but where does this result lie? This result lies in the numerator. So q to the negative 1/5 then has to be shifted to the denominator. Q to the negative 1/5 will move to the denominator to make the exponent positive. We end up with 1 over q to the 1/5 power. So notice, after subtraction, the result lies in the numerator. If the exponent is positive, leave it alone. But if after subtraction we get a negative exponent, we then have to shift this to the denominator so that the exponent is positive. Now let's write final answers in radical form. Notice that this is 1 over the 5th root of q to the first power. Now, remember we cannot have, okay, so no negative exponents in final answer. We've gotten rid of the negative exponent. What else? we have to rationalize all denominators, which means get rid of any radicals in the denominator. Notice we have a radical in the denominator, so we're looking at 1 over the 5th root of q. And the question is, how can we get this root out of the denominator? Well, remember we multiply by another 5th root. Okay, remember that the index must match. So we ask ourselves, we want to create, well, we're going to do this to the top and the bottom, so let's go ahead and put a 5th root on top. We want to create a group that can come out. So we need a total of how many q's? Well, we need 5 total. How many q's do we have already? Well, we only have 1. So how many more are we going to need? We're going to need 4 more. So we're going to multiply by the 5th root of q to the 4th, the 5th root of q to the 4th, and this ends up as a final answer of 5th root. We multiply this together. 1 times anything is itself. 5th root of q to the 4th over, on the bottom we get the 5th root of q to the 5th power, and now we can take a group of 5 q's out, leaving us with a final answer of the 5th root of q to the 4th. And if we take a group of 5 q's out, we're left with just 1 q on the outside and no q's left underneath, so we don't write the radical, and this is our final answer. Now, all right, so now we're going to look at more complicated problems. But, well, maybe do this. I'm going to split this video into a different video, so the next video, I guess, will cover maybe the more complicated examples. But before we leave this video, let me talk to you guys about the difference between radical form, exponential form, and simplified radical form. Okay, so giving you an example, if I write q to the 3/5 power, q to the 3/5 power is called exponential form. There are 3 forms that you're accountable for on your SOL. Exponential form. Now, if we convert this to radical form, this is the 5th root of q to the 3rd. Now, let me show you another example, and we're going to illustrate the difference between radical form and simplified radical. So if I write q to the 7/5 power, this is the 5th root of q to the 7th power. So here we have our exponential form, and here we have our radical form. Now, on the first problem, since the numerator was smaller than the denominator, notice when we get here we cannot take out a group of 5 q's, so we're done. This is simplified. So we're going to say that this is not only radical form, but this is also our simplified radical form. So this form that we're looking at is radical form and simplified radical form. So both forms are the same. However, on this problem, the bottom problem, since our numerator is larger than our denominator, we write this as the 5th root of q to the 7th. This is our radical form, but now we have to take out a group of 5 q's because we have 7. We take out a group of 5 q's. We have 1 q on the outside, and underneath the 5th root, since we took out 5, there's only 2 left. So we end up with q squared underneath, and this is called our simplified radical form. And you are accountable for all 3 forms on your SOL, or simplified radical form, not plural. Okay, so simplified radical form, and exponential form. However, on the first problem, exponential form converted to radical form, since no groups could come out, the radical form is the same as the simplified radical form. So question, if I write x to the 3/2 power, this is called what? This is called our exponential form. I'm just going to abbreviate EF. We're going to write this as the square root of x to the 3rd. Notice that our index is 2, which lies on the bottom. The square root of x to the 3rd. This is our radical form. And now to get to simplified radical form, we have to ask the question, can we take out groups? Okay, so we take out a group, yes, we're taking out groups of 2. There are 3. We take out a group of 2 x's. We end up with an x on the outside. What's left under the root? Just 1 x. So this is our simplified radical form. However, if I write x to the 2/3 power, this is our exponential form. And we notice that this is cubed root of x squared. And since we've converted, this is radical form. And now we ask the question, can we take out a group? No. Since our numerator is smaller, we cannot take out, we look here in our radical form, it makes sense. We're trying to take out groups of 3. We cannot take out a group of 3x's, so our radical form is the same as the simplified radical form because this form is considered to be simplified because no groups can come out. So let's conclude this video, and I will finish the topic of exponential form on the next video. All right, great. Good luck on your homework, guys.